All right, the topic of this lesson is vectors. Now, a vector is a quantity that has both magnitude and direction. All right, so there are many quantities in the world, but there are some quantities which are not completely defined unless you have both magnitude and direction. Those quantities are called vector quantities. How do we represent a vector? First of all, if um, if you have, for example, let's say AB and an arrow over it, that reads the vector AB. That reads the vector AB. Now, a vector may be represented by a straight line with an arrow. A vector may be represented by a straight line with an arrow. The length of the line is a measure of the magnitude, and the arrow indicates the direction. The length of a line the length of the line is a measure of the magnitude, and the arrow indicates the direction. All right. So the length of the line, is a measure of the magnitude. So if you have a long line, it means that you have a vector with a big magnitude. If you have a short line, it means that you have a vector with a small magnitude. The arrow indicates the direction. Now, remember I said earlier, if you have AB like this with an arrow over it, that reads the vector AB. Now, if you put two strokes at the sides like that, that means the magnitude of vector AB. And remember, the magnitude of the vector is the length of the line. So the magnitude of vector AB, I'm going to call it R. R squared is equal to x squared plus y squared. All right, so that's Pythagoras theorem. The opposite of square is square root. So R would be equal to x squared plus y squared. So the magnitude of a vector, the magnitude of vector AB, R, is given by the formula R is equal to the square root of x, the square root of x squared plus y squared. All right, we'll get back to the whole issue of the magnitude of a vector. All right, theta in the diagram. Theta is the angle the vector makes with the horizontal, and it is an indication of the direction of the vector. Theta is the angle the vector makes with the horizontal, and it is an indication of the vector. All right, so this is a right angle triangle. The side in front of the angle, y, is opposite, and x is the adjacent. Now, the trig ratio that includes opposite and adjacent is tan. So tan theta is equal to opposite, which is y, over adjacent x. Therefore, theta would be equal to tan inverse y over x. Theta would be tan inverse y over x. What is theta? Theta is the angle that the vector makes with the horizontal. Now, a vector may be represented as a column matrix. A vector may be represented as a column matrix. So the vector AB could be represented by the matrix, the column matrix XY. The vector AB could be represented by the column matrix XY. Now, in moving from A to B, in this diagram here, in moving from A to B, X is the horizontal shift. So I'm moving from A to B. In moving from A to B in that direction there, in moving from A to B, X would be the horizontal shift and Y would be the vertical rise. X would be the horizontal shift and Y would be the vertical rise. All right. So X is negative if you're moving to the left, and X is positive if you're moving to the right? All right, that's something to remember. X is negative if you're moving to the left, and X is positive if you're moving to the right. Y is positive if you're moving up, and Y is negative if you're moving down. A vector is also represented by a common letter. So the vector AB could be the vector A. So is the vector AB is the vector common A, which is the column matrix X, Y. The vector AB is the vector common A, and it is also the column matrix XY, where X is the horizontal shift in moving from A to B, and Y is the vertical rise. All right, let's have a look at this example. Now we're asked to express the following vectors in the form AB. All right, let's look at the first vector. The first vector is AB, the vector AB as a column matrix. All right, in moving from A to B, um, I would have moved what? Horizontally, 1, 2 units to the right. So the horizontal movement goes to the top, and I would have moved vertically 1, 2, 3 units upwards. So that value goes to the bottom. The 3 goes to the bottom. So AB would be the vector 2, 3. AB would be the vector 2, 3. So, and all that is saying is that is moving from A to B, I moved 2 units right and what? 3 units vertically upwards. Remember, if you're moving from, if you move into the, if you move horizontally to the left, the value must be negative. If you move to the right, the value must be positive. Vertically, if you move up, the value is positive, and if you move down, the value is negative. All right, let's talk about the vector CD, the vector CD. All right, CD, in moving from C to D, I move right and I move down. All right, moving from C to D, I would have moved 1, 2, 3, 4, 5 units right. The horizontal movement goes to the top, and I move 2 units down. So that's minus 2. Remember, if you're going down, the unit must be negative. All right. A, B, C, D, E, F. Let's go for E, F. All right. In moving from E to F, I would move to the left and then up. All right. In moving from E to F, I moved 1, 2, 3, 4 units 4 units to the left, so that's minus 4. So that's minus 4, and 1 unit up, so that is positive 1. All right. Next is GH. Moving from G to H, I move to the left and down. I move 1, 2, 3. I moved 1, 2, 3 units to the left, so that's minus 3, and 2 units down, 1, 2, so it's minus 2. Um, let's go for IJ, IJ, the vector IJ. All right. In moving from I to J, I only move horizontally. and I move horizontally to the right. 1, 2, 3, 4 units. So move horizontal to the right 4 units. So that's 4 unit goes to the top. I didn't move vertically at all, so the vertical movement is 0. Next we have what? KL. KL, the vector KL. In moving from K to L, I only move vertically downwards. So there was no horizontal movement. So the horizontal movement, which is the top value, is 0. And the bottom value is 1, 2, 3, 4, 5 is -5. If you're going down, that value has to be negative. So what must you remember? If you are representing a vector as a column matrix, um, the top value represents horizontal movement. The bottom value represents vertical movement. Horizontal, if you move to the left, that figure must be negative. And if you move to the right, the figure must be positive. Vertically, if you move up, the number is positive. And if you move down, the number is negative. All right, equal vectors. Two vectors are equal if they have the same magnitude and the same direction. They have the same magnitude and the direction. Remember with vectors, the length of the line is an indication of the magnitude, and the arrow indicates the direction. All right, in the diagram to the left, AB is the vector. AB is the vector. It's represented as a column. It's 1, 2, 3, 4 right. So it's 4 right, and what? 1, 2, 3, 4, 5 up. So it's the vector 4, 5. AB is the vector 4, 5. All right. Let's go for CD. To get from C to D, we're going to move 1, 2, 3, 4 units to the right, and 1, 2, 3, 4, 5 units up. So this is the vector 4, 5. All right. So if you look carefully, both the vector AB and the vector CD are represented by the same column matrix. AB and CD are equal vectors. Why? Because they both have the same magnitude and the same direction. All right. Remember the magnitude R. The magnitude R is the square root of the x coordinate plus the y coordinate squared, and the direction indicated by theta is equal to tan inverse y over x. So if if two vectors have the same column matrix, it means that they will have the same magnitude and the same direction, because the x and y values are the same. If they have the same magnitude and the same direction, those two vectors are equal vectors. All right. The diagram to the right is a parallelogram, and in this diagram, um, the vector the vector AB is represented by common A, and the vector AD is represented by common B. Now, the vector BC, um, now this is coming straight from property of a parallelogram. For a parallelogram, opposite sides are equal and parallel. Opposite sides of a parallelogram are equal and parallel. Now, the fact that the opposite sides are parallel, it means that the two sides are basically heading in the same direction, and the two sides are of equal length. So it means that the two sides have the same magnitude. So if vectors are on opposite ends of a parallelogram, if two vectors are at opposite ends of a parallelogram, um, and the arrows are heading in the same direction, the two vectors are equal vectors. So the vector AB is equal to the vector DC, and both of them equal to the vector A. It is also true about BC. AD is equal to BC, and they're both equal to vector what? B. So vectors on opposite sides of a parallelogram with the arrows going in the same direction are equal vectors. Why? Because they have the same magnitude and the same direction. Why the same magnitude? Because opposite sides of a parallelogram are equal in length, and the same direction because opposite sides of a parallelogram are parallel. All right, inverse vectors. Inverse vectors have the same magnitude but opposite direction. Inverse vectors have the same magnitude but opposite direction. The vector AB, all right, let's write this up here. The vector AB would be the vector 1, 2, 3, sorry, 3, 4, no, it's 3 actually, 3, and then 1, 2, 3, 4, 5. So AB would be the vector 3, 5. CD would be the vector 1, 2, 3, minus 3, and 1, 2, 3, 4, 5. So it would be the vector minus 3, minus 5. All right, the negative is common, so we can get it out. This is minus the vector what? 3, 5. All right. So basically what we can see is that the vector, what we can see is that the vector CD is equal to minus the vector AB. And the converse is also true, that the vector AB would therefore be equal to minus the vector CD. All right, so the minus there is just simply indicating that the two vectors are going in what? In opposite direction. So the two vectors have the same magnitude, because once you have the same column matrix, they have the same magnitude. And the two vectors have the same magnitude, but they have the opposite direction. In the diagram to the right, PQ is the vector A, PQ is the vector common A, QP is the vector minus A. Why minus A? If the vector is positive going from P to Q, going in the opposite direction from Q to P, it would be negative. So the vector QP is equal to minus the vector PQ. All right. All right. This is a fact that is going to come in extremely handy when you start working on questions. So if you have two vectors that have the same magnitude but have opposite direction, the two vectors are inverse vector, and one vector is the negative of the other vector. And the negative there is simply saying that they're going in opposite directions. All right, scalar multiple, parallel lines, collinear points. Parallel vectors are scalar multiples of the same base vector. Parallel vectors are scalar multiples of the same base vector. All right, so we're going to see that in a second. Two vectors are collinear, and the word collinear means in the same straight line if they are parallel and they share a common point. So if two vectors are parallel, how would we know if they're parallel? They're parallel if one is a scalar multiple of the other, and So if they are parallel and they share a common point, the two vectors are in a straight line, the two vectors are said to be collinear. All right. Um, let's just go through very quickly here. From my diagram, the vector PQ would be the vector PQ would be the vector 2, 3. Why? Because in moving from P to Q, I move what? 2 units to the right and 3 units up. Now the vector RS would be 1, 2, 3, 4, 4 at the top, and 1, 2, 3, 4, 5, 6, 6 at the bottom. So RS would be the vector um, 4, 6. So both 4 and 6 can be divided by 2. So 2 is a common factor. So I'm going to get that 2 out on the outside. 2 into 4 is 2. And 2 into 6 is what? Is 3. All right. So what we can see here is that the vectors PQ and RS have the same base vector. And that base vector is the column vector 2, 3. But the vector RS is 2 times the vector PQ. So the vector RS is 2 times the vector PQ. PQ is the column vector 2, 3, and RS is what? 2 times the column vector 2, 3. So the vector RS is 2 times the vector PQ, and the vector PQ is a half of the vector RS. So what we can say is that PQ and RS are scalar multiples of the same base vectors. Now, when two vectors are scalar multiples of the same base vector, we say that those two vectors are parallel. So the vector PQ and the vector RS are parallel. All right. Up top. All right. Let's have a look at the vector LM. All right. So M is a point on Ln such that Lm is 1/3 of Ln. Lm is 1/3 of Ln. So it is M is 1/3 of the entire vector Ln. Now if Ln is the vector A, Lm, which is 1/3 of Ln, would be 1/3 of the vector A. So the vector Lm would be 1/3 of the vector A. Mn, which is the lower half down here, Lm, which is the lower half, would be 2/3 of what? Ln, and therefore it would be 2/3 of A. All right, back over to the left diagram, and now let's have a look at TUV. All right, so here is where U is. TU as a column matrix would be 3, 2. UV would be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4 would be 6, 4, which would be 2 is a common factor, 3, 2. So UV, the vector UV is 2 times the vector TU. All right. Oh, um, so one more thing I wanted to share that I didn't say. Well, I did say it earlier, but I need to emphasize it here. From this diagram, it is clear that T, TU and V are in a straight line. From a point of view of vector, how is that shown from a point of view of vectors? All right, first of all, I said earlier that two vectors are in a straight line if one, they are parallel, and two, they share a common point. All right. And the vectors TU and the vector UV are parallel. Why are they parallel? They're parallel because they're both what? Scalar multiples of the same base vector, which is 3, 2, and they share a common point. The point that they share is U. You have TU and you have what? UV. When two vectors are parallel and they share a common point, we say that the two vectors are in a straight line. All right. So T, U, and V would be collinear. All right, let's check out the next page. All right, so this is again something I was saying. Here, back to the LM diagram. That's that diagram here at the top. This diagram here. Back to this diagram. That's the diagram they're looking at. All right. Ln is equal to A. Lm is 1/3 of ln, so it's 1/3 A. And Mn is 2/3 A. So all of that means that what Lm and Mn are scalar multiples of the same base vector A. One is 1/3 A and one is 2/3 A. So that basically means that Lm and Mn are parallel. Two vectors are parallel if they if they're scalar multiple of the same base vector. The point M is common because you have Lm and Mn. So the point M is common. So therefore, since the two vectors are parallel, the two lines are parallel, and they share a common point, L, M, and N are collinear. Triangle law of vectors. Now, if two vectors are acting in the same clockwise or or anti-clockwise direction, the sum of the two vectors may be obtained by completing a triangle. Triangle law of vectors states that if two vectors are acting in the same clockwise or anti-clockwise direction, the sum of the two vectors may be obtained by completing a triangle. All right, we'll get triangle law of vectors is extremely important as it relates to solving vector questions. Parallelogram law of vectors is also important, but maybe not as important. If two vectors are acting in opposite directions, so that would be one is acting in a clockwise direction and the other is acting in an anti-clockwise direction, the sum of the two vectors may be obtained by completing a parallelogram. So let's have a look at the first one. All right, triangle law of vectors. Now, essentially, triangle law of vectors. So here we have two vectors. Two vectors are the vector AB, and AB I would say is acting in a clockwise direction. It's acting in a clockwise direction. And we have BC. So we have two vectors both of them acting in a clockwise direction. Now, the sum of the two vectors can be obtained by completing a triangle. So the line that completes a triangle is the vector what AC. Now the vector AC is called the resultant vector. What about it? Well, for starters, it acts in the opposite direction. Both AB and BC are going in a clockwise direction, and AB and BC in a clockwise direction, and AC is going in an anti-clockwise direction. According to the triangle law of vectors, AC is equal to the vector AC is equal to the sum of vector what? AB and plus what? BC. This is the triangle law of vectors. All right, let's straighten up that. So that is the triangle law of vectors, and it's something that we could show. So triangle law of vectors, that is a straight theory. It's something that we could test. Um, so let's test it. AC in column matrix form. AC would be 1, 2, 3, 4, 5, 6. Would be 6 horizontal and 6 horizontal and 2 vertical. So AC would be the column matrix 6, 2. All right. Now AB is by now you should be able to do this on your own. AB is 3, 3, 1, 2, 3, 4. AB is 3, 4, and BC is 1, 2, 3 is 3 minus 2. Now, if the triangle law of vectors is correct, when I add these two vectors, if the triangle law of vectors is correct, when I add these two vectors, I should get AC, which is what? 6, 2. If the triangle law of vectors, so up here is just straight theory. Up here is theory. This is a theory. Triangle law of vectors says that if two vectors are acting in the opposite direction, are acting in the same direction, the sum of those two vectors can be obtained by completing a triangle. That is theory. Down here now, down here, we're trying to see if that is correct or not. How are we testing it? We're finding the vector AB and the vector BC, and we're going to add them together. And if when I add them together, I get AC, which is 6, 2, it means that the triangle of vectors is correct. So let's add them. So this would be the vector AB, which is what? 3, 4, plus the vector BC, which is 3 minus 2. 3 plus 3 is what? 6. We're adding matrices. When matrices of the same order may be added together by adding corresponding elements. And 4 plus minus 2, 4 plus minus 2 is what? Is 2. So according to this, the triangle law of vectors is correct. If two vectors are acting in the same direction, the sum of the two vectors may be obtained by completing a triangle. So if this was, let's say, the vector A, and this would say, let's say, the vector B, this would be the vector A plus B. All right. So if AB is the vector A and BC is the vector B, AC would be the vector A plus B. Parallelogram law of vectors. All right, parallelogram law of vectors. All right, parallelogram law of vector essentially says that if two vectors are acting in opposite direction, so here of this vector PQ is acting in a clockwise direction, and PR is acting in an anticlockwise direction. So we have two vectors are acting in an anticlockwise direction. The parallelogram law of vectors says that we can find the sum of these two vectors by completing a parallelogram. All right, so let us complete a parallelogram. PQ is what? 1, 2, 1, 2, 3, 4, 5. Remember, opposite sides of a parallelogram are equal and parallel. So since PQ is what? Is 2, 5. The side over here must also be from R must be 2, 5. So it's 1, 2, 1, 2, 3, 4, 5. So that's the next point of the parallelogram. All right, so we have what? PQ. Let's change this to, all right, PQ. Let's call this PQ and R. So let's call this S. Let's call this S. All right, so let's complete our parallelogram. Opposite sides of a parallelogram are equal and parallel. All right, so the resultant vector, blue, and let's make it be green. Let's increase this. All right, so this would be the resultant vector, which will be the sum of the two vectors. All right. All right, so that's the vector PS, and this right here, this is the parallelogram law of vectors. All right, and essentially the parallelogram law of vectors says that if two vectors are acting in opposite direction, in opposite direction, the sum of the two vectors can be obtained by completing a parallelogram. So if this is the vector A and this is the vector B, PS would be the vector A plus B. All right. RQ, let's connect R and Q. Change by the color. RQ, let's change it to Tinder. RQ is actually equal to PQ minus PR. So this will be RQ. RQ, the vector RQ. All right, so I didn't put the vector symbols above them. Parallelogram law of vectors. All right. And of course, we could prove all of this, all right? But we could probably show this from triangle law of vectors. RQ from triangle law of vectors. RQ would be equal to RP plus PQ. All right, that's triangle law of vectors. But RP is equal to minus PR. All right, their inverse vector. So if going from P to R is positive, going from R to P would be is negative. So going from R to P is actually minus PR plus PQ. If I put the positive one first, this would be PQ minus PR. All right, and that is RQ. All right, so for parallelogram law of vectors, the sum of two vectors acting in opposite direction could be obtained by completing a parallelogram. All right, so this would be the sum, PS would be the sum, and RQ would be the difference. So let's move this up a little. All right, so that's parallelogram law of vectors. Something again that I'm quite sure could come in handy. Position vector. A position vector is a vector that is tied to the origin. A position vector is a vector that is tied to the origin. All right, and this is something you're going to see in operation. This says if A is the point 2, 3, then the position vector OA would be the column vector 2, 3. So essentially, the coordinate and the position vector of that point, the coordinate of a point and the position vector of that point have the same what values 2, 3. Here's an example. Given um, P, given that P is the point 2, 5 and Q is the point 4, 1. So P is the point 2, 5 and Q is the point 4, 1. We're asked to determine the vector, PQ. All right, to do this, we're going to use position vectors. All right, so first of all, let's identify the point 2, 5. So that would be 2 vertical, 2 vertical and 5 horizontal. All right, let's see if we can straighten up these so we can get the point proper. All right, so in other words, that's a point P, and P is the point 2, 5. Q is the point 4, 1. It's 4, 1. So this is where the point Q is. All right, so let's remove the lines. All right, so those lines only help us to identify where the points are. All right, so if that is a point P and that's a point Q, um, this line here, this would be the position vector OP. All right, undo. Now this would be the position vector OP. A position vector is a vector that is tied to the origin, and this would be the position vector OQ. All right, and this would be the vector PQ. All right. So, all right. So we're given so first of all, P is the point 25. So OP would be the position vector 25. So the position vector and the coordinate have the same values. Q is the point 41. So the position vector OQ would also be 4, 1. All right. And now we're asked what? Determine the vector PQ. Right? PQ is actually called a displacement vector. All right. Using triangular vectors, PQ would actually be equal to PO. So you go from P to O. PO from P to O plus what? OQ. So this would be PO plus OQ. This triangle law of vectors. All right. But we don't have PO. What we have is OP. So PO is actually minus OP. So if going in this direction is positive, going in the other direction, which is from P to O, would be negative. So this is minus OP plus OQ. Now minus OP would be minus 2, 5 plus OQ, which would be 4, 1. So this would be minus 2 plus 4 minus 5 plus 1. And therefore PQ, the vector PQ, would be the vector 2 minus 4. All right, so that's how you would have used what position vector to determine the displacement vector PQ. What else I want to say here? All right. So what we just did is that we just found this using calculation, and I'm quite sure everybody knew that you probably could have found it using using the fact that you went 2 units to the right, and from 5 to 1, 4 units down. All right. So the next thing we're asked to find is the magnitude of PQ of vector PQ. Now the magnitude of vector PQ would be equal to the square root of 2 square plus minus 4 square. That would be the square root of 4 plus 16. This would be the square root of 20. And this would be about 4.47 units. So the magnitude of PQ, the magnitude is the length of the line. We looked at this formula, which is basically just Pythagoras theorem earlier. All right, so the magnitude is 4.47 units. All right, You probably could take a break here, pause before we get into this question, because this question, we'll have a little bite. All right, so this question is taken from the May 2008 paper. It's question number 13. It says the position vector of A and B relative to the origin, position vectors of A and B relative. So this question is taken from May 2008, question number 13. It says the position vectors of A and B relative to the origin are A and B respectively. The point P is on OA such that OP is equal to 2 times PA, and the point M is on BA such that BM is equal to MA. A. Copy the diagram and complete it to show the points of P and M. Alright, so let's start the question. Alright, so this is a blow up of the diagram. Alright, we're told that the point P is somewhere on OA. So this is the line OA. Somewhere on this line is the point P. Alright, such that OP is equal to 2 times PA. Alright, so essentially what this is saying is that it's like OA is divided into 3 parts, and OP is 2 parts of the 3, and PA would be the next part. Alright, so if I'm imagining that it's divided into 3, OP, P would be about here, such that OP would be 2 times PA. Alright, if you look good, you can see it's roughly about that. And M is on BA, so M is somewhere on this line. M is on BA, such that BM is equal to MA. So M should be in the middle. So this would be the point M, such that BM is equal to MA. Both sides are the same length. Alright, so we just completed A. We copied the diagram and we inputted M and P. Next, we're told that OB is produced to N. All that simply means is that the line OB is extended to N. The line OB is produced to N such that OB is equal to BN. Alright. Show the position of N on your diagram, and you're to express in terms of A and B the vector AB, PA, and the vector PM. Alright, so let's get to that part of the question. Alright, so the line OB is produced. And what I said earlier is that all that simply means is that the line is extended. All that simply means is that the line is extended. So let's extend it. So OB is produced, is extended to N such that OB is equal to BN. Those two lengths must be the same. It's the same straight line, but it is produced, is extended. The word produced there simply means extended. Alright, so we've just indicated N. Then we're asked to express in terms of A and B, the vector AB. So, all right, this is A and this is B. So we want the vector AB. All right, using triangle law of vectors, AB would be equal to AO. So you go from A to O and then from O to B. So it's AO plus OB. Now, OA is A, OA is A, therefore AO would be minus A. So if going in this direction is positive, going in the other direction would be negative. All right, and OB would be B. All right, I sort of like turn them around, so let's turn them around so that the positive is first. So this would be B minus A. All right. Next we need the vector P, the vector PA. All right, the vector PA. Well, this one's supposed to be easy. Remember that by putting in P on the line OA, effectively what we did was divide it into three equal parts. 1, 2, 3. The entire vector from O to A is A. OP would be 2/3 of A, and PA would be 1/3 of A. PA is 1/3 of A. And then lastly, we need PM. PM. PM, triangular vectors. To get from P to M, we're going to go from P to A and then from A to M. All right. So PM would be equal to PA plus AM. All right. And this is triangle law of vectors. PA, we just discovered it is 1/3 of A, and AM is a half of AB. AM is a half of AB, so AM is a half of B minus A. Remember, AB is B minus A, and AM is a half of AB, so AM is a half B minus A. All right. I sort of need some space. So let's try and create some a little. All right. Try and create a little space, just a little. All right. Let's us find an LCM here. I wonder if we need to simplify. Yeah, let's simplify. The LCM is 6. 3 into 6 is 2. 2 times A is 2A. 2 into 6 is 3. 3 times B is 3B minus 3A. So PM would actually be equal to 1/6. And at the top, it's 1/6. 3B. 2A minus 3A is minus A. It would be 1/6 3B minus A. All right, and that would be PM. All right, sort of tight. Yeah, we started doing something else different on the next page. All right. So what is the last part? Definitely you guys can sort of go back over this section on your own. Go back over this section on your own. You can see that the math that I use is quite sound, and what I did is correct. All right. And the last part of the question, asks us to C, use a vector method to prove that P, M, and N are collinear. Use a vector method to prove that P, M, and N are collinear. All right. So we want to prove that P, M, and N are in a straight line. We want to prove that P, M, and N are in a straight line. All right. Earlier we said that the way you prove that two vectors are in a straight line is that you have to first prove that two vectors are parallel, and one and two um, that they share a common point. Once they're parallel and they share a common point, we're good. All right, so it's P, M, and N. We just found PM, and for PM we got 1 6 3b minus a, 3b minus a. All right. So let us get mn now. Mn, the vector mn. From triangle of vectors, mn would be mb plus bn. All right. Now mb is equal to a half of ab, which is equal to a half of b minus a, and bn is actually equal to b. Why? Um, because remember earlier we said that what OM N is produced so that BN, that OB is equal to BN. So those two they're in the same straight line, meaning therefore they are parallel, and they have the same magnitude because the same length, therefore they are equal vectors. So if OB is B, BN is also B. So it means that MN would be the vector MB, which is a half B minus A plus B. I'm going to put this over 1. The LCM is 2. 2 into 2 is 1. 1 times B minus A is B minus A. Plus 1 into 2 is 2. 1 into 2 is 2. 2 times B is 2B. So this would be equal to 3B minus A over 2. Alright? And this is just another way of saying a half of 3B minus A. Alright. So therefore we're sort of ready to make our statement. Our so we're asked to show that P, M, and N are collinear. This is my statement. My statement would be PM, which is the vector 1 6 3B minus A, is parallel to mn, which is the vector a half 3b minus a, and m is common, therefore p, m, and n are collinear. All right, so that takes care of b. All right, I think I'm going to insert a page to answer the last part of the question. All right, other page. All right, go back. So let's have a look at the last part of the question. All right, so D says we're to calculate the length of AN, and we're told that A is 6'2" and B is 1'2". So D, A is 6'2" and B is 1'2", and we're to calculate the length of AN. We're to calculate the length of AN. All right. To get from A to N, what are you going to do? That's AN, and we're asked to calculate the length of vector AN. Well, first of all, if you're going to calculate it, you have to first find out what is the vector AN. AN, triangle of vectors, you go from A to B, and from A to B, and from B to N. That's the shortest way. So triangle of vectors, AN is equal to AB plus BN. Triangle of vectors. AB is B minus A, found that out earlier, plus BN is B. B plus B is 2B, so this is 2B minus A. So that's AN. Alright, in column matrix form, this is 2 times B, which is 1, 2, minus A, which is what? 6, 2. So multiply all the numbers inside here by 2, so it's 2 times 1, which is 2, and 2 2's, which is what? 4. Minus, which is minus 6 minus 2. So this is minus 4, 2. Now the magnitude of AN is therefore the square root of minus 4 squared plus 2 squared. This is the square root of 16 plus 4, which is the square root of 20, which is 4.47 units. All right. So this question was a sort of like a long-winded vector question. Very interested, something that you can go over, have a look at it, go over it. We'll look at one more before we end the class. All right, this is question number 15 from your workbook. You don't have this, but I'm gonna send it to you. It says the diagram below shows the position vectors of two points A and C relative to an origin O, you're asked to copy and complete the diagram to show I the point B such that OABC is a parallelogram, and you're also asked to identify the vector U, where U is equal to the position vector OA plus the position vector OC. So let's get to the diagram. Let's get to the diagram and answer that question. All right, so we're to copy the diagram. So this is my copy. I'm guessing you can do your own copy. All right, if it's a parallelogram, the side OC is 4 units. So the side AB must also be 4 units. So this would be 1, 2, 3, 4 units. So B must be here. Why? Um, Basically because opposite sides of a parallelogram are equal and parallel. Alright, so B would be up here. Alright, so if OC is vertical and it's 4 units, it means that AB must also be vertical and also 4 units. Why? Again, opposite sides of a parallelogram are equal and parallel. So now that I know where B is, I can complete the parallelogram. Alright, as instructed. Alright, so I've completed the parallelogram to put in. So next, I must put in next I need to put in U, and U is a vector which is OA plus OC. Alright, we did this largely earlier, and this is the vector OA, and this is vector OA, and this is the vector OC. The two vectors are acting in opposite direction, so you can find the answer by completing a parallelogram. They already asked us to do that, so we can just basically put in U. U is actually OB. Alright, so this is the vector U. This is the vector U. That's the vector U. Alright, why? Because from parallelogram law of vectors, the vector OB is the vector OA plus what? OC. And since OA plus OC is U, it means that OB must be U. Alright, so that's the first thing we're asked to do. And was it difficult to do it? We did it. Alright, so that was A. Then we're asked to express as a column vector in the form XY, the vectors OA, OC, and AC. Alright, so we're at B. BI. We need OA. Alright, we've done this many times already. It's a position vector. OA is the point, A is the point 6, 2. So OA is the position vector 6, 2. Plus, we could also show it very easily. This is 1, 2, 3, 4, 5, 6 to the right, and 1, 2 up. So OA is the vector 6, 2. Alright, we need OC. OC is just vertically upwards. there's no horizontal movement. So the horizontal component is 0 and the vertical component is 4. OC is 0, 4. Lastly, we're asked for AC. AC. All right, I'm guessing we could get it from the diagram, or we could get it using parallelogram law, using triangular law of vectors. Either one is going to give us the answer. Let's put it in. All right, that's AC. All right, triangular law of vectors says AC would be equal to AO plus OC. AO is minus OA, so it's minus 6, 4 plus OC, which is 0, 4. Sorry, that should be 6, 2. So it's minus 6 plus 0 and minus 2 plus 4. So this would be minus 6, 2. All right. And we could have gotten that by just by observation as well. Because it is what? 1, 2, 3, 4, 5, 6, negative. 1, 2, positive. So we could have gotten it by observation, or we could have gotten it by calculation. All right, so that took care of B, the B part of the question. Let's move on to the C part of the question. C part of the question says, given that G is the midpoint of OB, G is the midpoint of OB, use a vector method to determine the coordinates of G. All right, so G is the midpoint of AB. This is G. G is the midpoint of AB. Or to use a vector method to determine the coordinates of G. Earlier, when we we're talking about position vector, we indicate that the position vector and the coordinate is the same thing. We demonstrated it also in this section. Um, A is the coordinate as coordinate 6, 2, and the position vector OA is also what, 6, 2. So if I wish to determine the coordinate of G, all I basically need to do is find the position vector OG. But here's what we're told. So we're in C. We're told that OG is equal to a half of what? OB. And OB, so this is a half OB, but OB was equal to OB here, which is U, is equal to OA plus OC. So it's equal to OA, which is what? OA, which is 6, 2, plus OC, which is 0, 4. All right. So this would be a half of 6, 6. A half of 6, 6 would be 3, 3. So the position vector OG would be 3, 3. If OG is a position vector 3, 3, it means that G is the point 3, 3. So we're asked to find the coordinates of G, which we just did. Then it says prove using a vector method that A, G, and C lie on a straight line. Prove using a vector method that A, G, and C lie on a straight line. All right. All right. So essentially we said that what if if two vectors form a straight line, the two vectors must be parallel and they must share a common point. So since it is A, G, and C, I need to find the vector. I need to find the vector AG because I already found the vector AC. I need to find the vector AG. I need to find the vector AG because I already know the vector AC. All right, AC is the vector minus 6, 2. So AC is the vector minus 6, 2. Now let's find AG. AG is the vector, triangle of vectors. It would be equal to AO plus OG. We found AO we know already. AO we know already. AO is opposite of OA, so it's minus 6, 2. So this is minus 6, 2. And OG is 3, 3. So this is minus 6 plus 3 and minus 2 plus 3. All right. So this comes out to be minus 3, 1. And AC up top here, 2 is common. You take out the 2 and you end up with what? Minus 3, 1. All right. So now I can make my statement that AC is parallel to AC is parallel to AG. How do I know that? I know they are parallel because they're scalar multiple of the same base vector. All right, that's one. And the point A is common. The point A is common. Is common. Therefore, A, G, and C are collinear. All right. Happy to say this is the end of the lesson. All right. Please do your homework on vectors, or please do the best that you can.